Okay, today we'll finish off the single cycle microarchitecture hopefully quickly and cover multi-cycle microarchitectures. My intent by the end of this week is to finish microcoding and start pipelining. And then we'll go quickly into how to improve performance using microarchitecture. So you'll see a lot of techniques very, very quickly. But I already reminded you that homework 1 is due today, and homework 2 is going to be out soon. And lab assignment, don't forget. It's going to be tedious, but you're going to have a lot of fun. This is just a warm-up lab. Later, you'll do very advanced things like coherence. OK. Look ahead. Lab assignment 2 will be assigned soon also. This will be in Verilog. You'll have a Verilog practice, which won't be turned in. This is just to brush up your Verilog. But hopefully, you don't need any brushing up. And lab assignment 2 itself will be due February 15th. So I'm giving you an advance notice 2 weeks, more than 2 weeks before it's due, right? This is going to be single cycle MIPS implementation in Verilog. Again, this is kind of a warm-up, and then we're going to move on to pipelined implementation of MIPS. Just a reminder, all labs are individual assignments. Please respect the honor code. There's no collaboration. Certainly, you cannot do the lab together. This is for you to learn how to design a microarchitecture or how to do everything related to the labs. And you will learn a lot more if you actually do it yourself. You can certainly talk with the TAs, go to the lab sessions. OK? There will be extra credit for lab assignment 2. This is just to give you a look ahead so that you can plan your time if you want to do more. So single cycle implementation is the normal implementation, but we'll see that single cycle is not a good abstraction for building machines. And you've already seen most of the reasoning for this, right, in the last lecture. Why wasn't that a good abstraction? Anybody remember? Why don't you want to build a machine that executes an instruction in a single cycle? Yes?
Because your clock has to be, can only be as fast as the slowest instruction.
Exactly, yeah, because your clock cycle time is now determined by the slowest instruction, which could be very, very, very slow, right? Especially if that instruction is very complex, right? Even if it's not complex, if you're accessing memory in an instruction, memory can take hundreds of nanoseconds, right? Or maybe milliseconds almost, depending on where that memory is. OK, so this is not a good abstraction, but this is to get you started. I mean, you have to start somewhere. This is your first processor for most of you. But if you want to do more, one extra credit will be, maybe we can add other potential extra credits when we get to the lab. You can implement the MIPS core using a microcoded design, more a multi-cycle microarchitecture. So this is where you can exercise your creativity a little bit. So we're not going to specify any details for this extra credit for lab assignment 2. You can come up with your own microcode format, and you can design your own microarchitecture. But the first step is completing the single cycle portion of the assignment. So this is just to give you some flexibility in designing a machine, similar to what we're going to discuss in class today and tomorrow. OK? And we'll specify this later on also. But for this extra credit, the microcode implementation should execute the same programs that your ordinary implementation does. And you should demo it by the normal lab deadline. And if you want to attempt this, we'll give partial credit on extra credit too. So even if your microcode implementation doesn't fully work, I encourage you to attempt the extra credit if you find the single cycle implementation too easy, or if you figure out that you're already done with the single cycle implementation within a week or so, which could be true. But this will require a lot of debugging. OK? OK, that's a look ahead. You're not even done with the first lab yet, but it's good to figure out what's coming so that you can plan your time. OK, these were the readings for today. Hopefully, you've done most of it. There's another look ahead reading for a next lecture. This is for next week. We're going to cover pipelining, so any reading that you do on pipelining would be useful. And this is the chapter. And you can get the reminder, you can get the ebook for the Patterson and Hennessy book online. Not online, from the library reserves. So you can access it online. OK, last lecture review. Single cycle microarchitectures. We've covered them, and we're going to finish them off today. but I'll ask you some questions, I guess. What phase of the instruction processing cycle does the MIPS jump and link instruction exercise? You guys remember the jump and link instruction? Yes? No? Yes, you remember. That's good. I don't remember, but but I can figure out, right? That's my cheat sheet. So what does jump and link do? Anybody who remembers can tell me? Yes.
It jumps to an address and then it stores the current PC plus 8 into R31.
That's right, yes. Basically, actually, it does the second one first, right? Logically. Yeah, that was the mistake I made on the board, and Justin corrected me last time. Basically, yeah, first it links the program counter plus 8 in R31. Basically stores R31 equals program counter plus 8. And then it it changes the program counter to a jump address. If you look at this, and then this specifies jump address as PC plus 4, comma, some immediate bits from the instruction, basically. I'm not going to write it here, but I'll just say bits from instruction. So the instruction needs to increment the program counter, store it into a register, calculate a jump address using the program counter and some immediate bits that's coming from the instruction itself, and store them into the program counter. Right? So what phases does this instruction exercise? Remember, what is a phase? The instruction processing cycle, right? You fetch the instruction, you decode the instruction to process an instruction, you evaluate the address of the instruction, fetch operands, and then execute the instruction, and then store result. Right? You know this by heart now, the 6 phases of the instruction processing cycle. Well, every instruction needs to be fetched. Right? So this instruction exercises that. Every instruction needs to be decoded. Otherwise, you don't know what to do with it. Evaluate address. Well, it looks like we're evaluating the address of this instruction, right? So this is, you can think of this as evaluation of the address. So, or this could be also, well, that's not exact. That's also an address, right, that you're storing. So this is where things become a little bit fuzzy. Yes?
But evaluate address is to evaluate an address where you fetch the operands from the memory.
That's right, yeah. You could view it that way. If you view it that way, then you don't do this part, right? At least for this instruction. But if you view this one as evaluating the address, then you do this part. So you can view it either way. Let's assume that that's part of the address evaluation. I'm not going to execute this instruction, I think. Fetch operands. I guess what are the operands of this instruction? Immediate, right? Well, I guess I'll do everything in this instruction for you. So you fetch the operands. So which is the immediate and the PC plus 4, right? And then you execute the instruction. I guess I will execute the instruction also, which is this part, right? You calculate a program counter. Does this instruction store result?
Not in memory.
Yes or no? Yes, which ones? Actually, it has 2 results, right? Almost. Well, this is the real register result, right? It's really storing a result into a register. So it goes through the store result phase also. So you could argue that this instruction exercises all phases of the instruction cycle, right? But you could also argue that if you're not, maybe it's not evaluating address. But I think you could go both ways on that one. This is just to give you an example of how an instruction is executed. There is no perfect answer for this question, actually. It's just to warm you up, showing that an instruction goes through these phases, and you can have instructions that exercise all phases. Okay? But don't forget this one. This is the store result part. you're actually storing the result into R31. And that's a result of the instruction. Make sense? OK. So this was an easy question, probably. OK. This is probably an easier question, maybe. How many cycles does it take to process an instruction in the single-cycle microarchitecture? 10. He's saying 1. OK. Which one's true? I guess 1, right? That's what single-cycle means. And you've already answered this question. What's the difference between data path and control logic? We'll cover this a lot today when we come to micro-coded machines. So data path consists of elements that operate on data, right? And control logic controls what those elements do to that data, right? Basically, how those elements are configured. I guess what's the difference between combinational versus sequential control? Anybody? Yes, combinational control is all hardwired, right? Sequential, you place the control signals in memory. And we will see this today when we cover the microcoded control. Do you guys remember this one? Last part of the lecture. What is the semantics of a delayed branch?
Always executes the instruction after a branch.
That's right. Always execute the next sequential instruction, even if the branch is taken. That's the semantics. And we've discussed this at the end of last lecture, so hopefully it was interesting. But this will become clear when we cover pipelining, a lot more clear. And we will cover a lot of other solutions to the branch problem. OK. And in fact, you will, in one of your labs, when you do the pipelining, one of your extra credit assignments will be implementing sophisticated branch prediction mechanisms. Okay. Well, when I say branch prediction, another alternative is when you get to the branch, predict whether it'll be taken or not taken. Right? And existing processors actually do that. Based on the past history of the branch, they can predict whether the branch will be taken or not taken, and depending on that, fetch the next instruction. So it's very sophisticated, right? And the question is, how do you predict that, right? Maybe you can think about how can you do a prediction on a branch. OK. OK, I'll leave these because this is what we talked about just now, right? These are just review parts. Data path, control logic. OK. I guess before I jump into today's lecture, I'd like to tell you how to make the best out of 447. Some of you asked me about this. Doing the readings would be useful, certainly. Like today's lecture, well, today's lectures doesn't work, right? This week's lectures will be easy to understand if you do the readings. Right? Actually, how many of you have done the readings? Appendix A and Appendix C. Be honest, right? OK, so it'll be a lot easier if you actually do the Appendix C. If you haven't done it by today, definitely do it by Wednesday. Because Appendix C is where you can get that, get the idea of how a microcoded machine works. I'll teach you in lecture, but readings also have their place. You can do them at your own pace, right? That way you can ask more in-depth questions and learn more, actually, if you do the readings. Well, I've said this many times. If you do the assignments early, this course will be a lot easier. And study the material and buzzwords daily. We're trying to help you as much as possible. Like my TAs are definitely taking the buzzwords every day, and they're pretty prompt in updating the website, right? So you can take a look at the buzzwords daily and lecture notes as well as videos. Videos have a delay associated with them, but are you guys finding that useful? OK, good. And take notes during class. Don't get limited to the buzzwords. And many of you are doing that, which is good. OK, now let's jump into today. We're going to finish single-cycle microarchitectures. I think I'm going to go very quickly because we've covered a lot of it. And then we're going to cover some basic microarchitecture design principles. Hopefully, this will be useful for the rest of your life. And we're going to take a look at how single-cycle microarchitectures pretty much violates all of them. And we're going to go a little bit more in depth into performance evaluation. Remember that slide that I showed you, flash forward? We're going to talk about that. And then hopefully we're going to talk about the best way of designing an automatic calculating machine, as Wilkes put it, microcoded machines, right? It's actually a beautiful way. I'm not sure if it's the best way. You can think about it yourself, but at that time it might have been the best way. Okay, remember this is the full single cycle data path we kind of formed with MIPS. You have this control logic that controls the data path elements, and control logic takes as input the instruction bytes. And you have the data path elements. So in your first lab, you're going to form the single cycle control logic, and I'm not going to go into this in detail, but you can think of a single cycle control logic as a combinational function of the instruction bytes, right? Basically, you take the instruction bytes and have a big combinational logic that provides you the control signals. That's what this control logic is. And your job in the first lab is to output the signals coming out of that combinational logic, as well as design that combinational logic. Right? So the question is, how do you do that? Well, it's simple. Basically, you go for every instruction you implement, you try to figure out what should be the output signals, right? What should be the signals controlling, what should be the value of each of these control signals? That's it. And then you design a hardwired logic that implements that functionality. Simple, right? So it's not that hard of a lab. And, well, you can, of course, minimize this logic afterwards. Then you can do it as a case statement also, but then the hardware will be very large, right? Or you could find commonalities between instructions and based on that minimize the logic. So I'll give you some examples. For example, we've covered the data path. One of the control signals is regdest. This basically selects whether the destination ID of the ID of the destination register comes from instruction bits 20 through 16 or 15 through 11, right? And what determines that? Whether the opcode is 0 or not. Right. Remember, if you go back to the data path, can you guys see this? Okay. There's this little mux here. It's controlled by this regdest signal, which I cannot read, but believe me that's the regdest signal. And this that signal determines whether the ID of the register comes from 20 through 16 bits of the instruction or 15 through 11 bits of the instruction. And whether or not the opcode is 0 determines that. Make sense? So that's how you control the data path elements. And mux is a data path element. There are other things, for example, ALU source. Whether the source of the ALU comes from the second general purpose register read port or whether it comes from the sign extended 16-bit immediate. And you can look at the data path element, which is this mux. I guess that's the ALU source control signal. And again, instruction bytes determine which input you take, I type versus R type, right? I guess branch also. Yeah, and this is the equation actually to determine that. I'm making your life a little bit easy. You can determine the equations from here. But this is not actually complete, so you may have to implement some other things. But this is just to get you started, right? Okay. Is this simple? Do we need to go through this in more detail? Probably not, right? Okay, I'm going to skip many of this, but you can do this. Basically, you're going to do this for every single control signal. Whether you write to a register write control signal. Do you disable it or enable it? Well, instructions that write to a register should enable it, right? Okay? Especially in a single cycle microarchitecture, that register write signal is asserted from the very beginning of the clock cycle, right? And hopefully at some point that value becomes generated. We're going to look at how these things change in multi-cycle microarchitectures. And multi-cycle microarchitectures will determine the control signals for the next cycle. Here you have a single cycle. So you just look at the instruction itself, not the cycle, not the state. Okay. Okay. I will not go through this in more detail. I'll let you figure it out. But don't forget the program counter also, which these are the control signals for the program counter updates. Where does the program counter let me get back to this. Oh, this didn't work. where I pressed the wrong button. Let me get back to this data path. PC source. There you go, this mux. This mux determines the input for the next program counter value. Basically, this program counter is always loaded with some value, and that value is determined by what instruction you're executing, right? If the instruction you're executing is not a jump, then you should get PC plus 4 somehow, right? So you actually have two muxes that determine that. Okay? And depending on what type of jump you have, you need to set these bits accordingly. Okay, and we've covered different types of jumps in the last lecture. So hopefully this should be easy. It should be fun. Who thinks that this is fun? Generating control signals. That's good, most of you actually. Well, somewhat maybe. It'll be more fun with the microcoded architectures, I think. With microcoding, it's a lot more fun. You're really programming the machine with microcoding. You'll see that. Here you're doing, actually here you're doing programming also, right? You're really programming how those data path elements are set up. It's the lowest level of programming.
Yes. So for the single cycle then, everything with the control signals are combinational? There's no FSM or anything?
Absolutely, yes. That's the beauty as well as the Achilles heel of the single cycle microarchitecture, right? Okay, ALU control is similar basically. You could do something like this, right? Depending on the opcode. If the opcode is 0, the ALU operation is selected according to this function. Remember that? If your opcode is 0, your function is specified at the bottom of the instruction bits. Or if your opcode is immediate ALU operation, you select the operation according to opcode. If it's a load, you select addition because you need to calculate address, right? Similarly, store, the function of the ALU should be addition again because you calculate address. If it's a branch, now it depends on the branch condition generation function, right? There are different branches that you're going to implement. If it's equal, then it's something, then you do subtraction, right? If it's not 0, then you do something else compared to 0, for example. So you'll have fun implementing this logic also. And other instructions that do not use the ALU, you don't care about what the ALU does, right? Okay, well, I guess you can see some of the branch conditions there. So let's take a look at, I guess, basically what you're doing is really generating the control signals that connect different parts of the data path components and that enable the data path components to do the thing that the instruction specifies them to do, right? For example, an R-type ALU operation, you do this. This is you're really programming these wires, right? So if you look at this, what does this mean? If you're executing an R-type ALU operation, let's see if I got this right. This is what you're connecting, right? You're connecting, this is the source register ID that you're connecting. This mux should select this one. And then register write should be set to 1 because it's an R-type ILU. You're writing to a register. This mux should select the destination register. Well, the general purpose, the second general purpose register to read, because it's not an I-type ALU, it's an R-type ALU. And then memory, well, ALU function should be coming from the bottom 6 bits of the instruction, right? And there should be some logic here that actually determines what the ALU should do, right? You're going to implement this logic. So control actually is not only this block, but also this block, right? Which includes the branch condition logic too. So if this is not a branch, you're going to select this function based on the opcode. That's actually, it's not only a branch, but based on this, you'll implement this logic. Okay? Well, you're not reading from memory or writing from memory, so you can set these to 0. Actually, you can set read from memory to 1, right? Because you're going to discard the result in the end. This mux should be choosing the output of the ALU because this is an R-type ALU operation. And R-type ALU operation basically increments the program counter, right? PC plus 4. You should select, this mux should select PC plus 4, and this mux should select PC plus 4 also. Okay? So these are the control signals that you need to set for an R-type ALU operation. Simple. I-type ALU, I'll let you figure out. Load word, I'll let you figure out. Store word, same thing. I guess in some cases, you can have don't cares. So if you're doing a store word, for example, because you're not writing to the destination register, you don't care what the destination register ID is, right? That way you can minimize the control logic if you actually use don't cares in your implementation. Similarly here, this mux, because you're not writing to a destination register, this mux's control signal can be don't care also, right? You don't care whether you select the memory output or the register output, or the ALD output. Okay? I guess branch not taken. Now here you need to implement the branch condition. And taken branch is a little bit different. You can see the difference is branch not taken is this, branch taken picks the target from here, right? The only difference is the output of that mux. Okay? Which output you select, which input you select to that mux, which determines the output, of course. And jump. Looks like there are lots of don't cares in jump, right? Because you don't really exercise this part. Well, you'd better not write to the register, though, or memory. So for each instruction, you'll need to figure out the control signals. Any questions? You can study this in more detail, and you're going to become very familiar with it anyway for Lab 2. But it's going to be fun. It's a lot of fun. This is a simple machine. Imagine the more complex machines that are implemented today. It's the same principles. You design some data path, and you control it. OK, now let's take a look at, I guess, what's in that control box. There are two ways of designing the control store, control logic. One is hardwired control, combinational logic. And you have no choice in a single cycle microarchitecture, right? It has to be, hardwired, combinational. The idea is control signals are generated combinational based on the instruction and what's going on in the data path. There's always interaction between the data path and control, as we will see in a microcoded architecture. The other option is to have sequential logic. This is sequential or microprogrammed control. And the idea here is to have a control store, have a memory structure that contains the control signals associated with an instruction. So you cannot do this in a single cycle microarchitecture, of course, but you index into this memory, and that gives you the control signals. At least most of your control signals. You basically take the instruction register, or parts of it, and index into the structure, and this structure tells you all of your control signals that control the data path. Okay? And this gets distributed into the data path elements. Now, modern machines actually employ both. Even if you have microcoded control, combinational logic is inevitable almost. Some functions are a lot easier to implement in combinational logic because you need interaction between the data path elements and control. And we will see this when we cover microcoded machines. An existing, I think I'll talk about it when I get to microcoded machines. But existing Intel and AMD and many other microarchitectures employ microcoded design to actually execute many instructions. But they also employ hardwired control. So we'll see that when we cover microcoded architectures. So let's evaluate the single cycle microarchitecture, although I think many of you are familiar with what we will do. So if you have a single cycle, is this a good idea, having a single cycle microarchitecture? No. I guess the answer is obvious now. When is this a good design? Or can this ever be a good design? It's always good to stretch your limits and think whether something is a good design at some design point, right? Is there a design point that makes it a good design? Yes?
Simplicity.
It is simple, but we'll get to that. I'm not sure if it's that simple. But there may be a design point where this is very simple. Yes.
You don't have to worry about deadlocks?
You don't have to worry about deadlocks. I guess that's true. Do you have to worry about deadlocks in other designs? If you design well? Yeah, yeah.
Maybe for elevator controller?
Elevator controller. That's a good, I don't know actually. So I was trying to ask actually, under what conditions would this be a good design? If your instructions are all balanced, this could potentially be a good design, right? If they all take similar amounts of time. Or if you have very, very few instructions. And if your memory is not, if the variance in terms of the time it takes to execute an instruction is very high, then this is probably a very bad design, right? Because you're determining your cycle time based on the worst case instruction execution time, combinationally. Whereas if that variance is very, very small, potentially this could be a reasonable design, right? Yes?
Will there be a design where you care more about fairness between instructions instead of total throughput?
That's a good question. I don't think you care about fairness between different instructions within an ISA, right? In the end, I guess you could argue that this could be, if you want a single cycle microarchitectures makes sense when all instructions take the same amount of time. Maybe.
I suppose it's more predictable. If you care about maybe having one instruction every cycle and have a very deterministic machine, where you cared about what comes out when.
I guess how long an instruction takes to execute. Yeah, maybe. It could be. But this is very hard to do, right? It's very hard to balance all those instructions to have takes the same amount of time. When is this a bad design? So most of the time this is a bad design in most realistic scenarios. So how can we design a better microarchitecture? And you know the answer to that, right? So let's analyze. Every instruction takes 1 cycle to execute. So CPI is strictly 1. Remember the CPI, cycles per instruction. And how long each instruction takes is determined by how long the slowest instruction takes to execute, even though many instructions do not need that long to execute, right? And you already know this. Critical path of the design is determined by the processing time of the slowest instruction. So I guess what is the slowest instruction to process, right? That begs the question once we make the statement. Remember the 6 phases? What is the slowest instruction? These are the 5 phases that we've gone through. Do each of these above phases take the same time to process all instructions? No, right? It's different. So let's take a look at the analysis of the data path. Even this is not going to be realistic for the design that we made. Assume that memory units take this much, ALU and adders take this much, register file takes this much, and assume that other combinational logic is 0 latency, which would be nice to have. But if you do the analysis, this is what you get actually for the critical path of different instructions, even with these optimistic assumptions. So the longest instruction is really a load word. You access memory twice and execute, write back, and decode. It exercises all of these phases in this case, depending on how you divide up these phases again. So delay is 600 picoseconds with these assumptions, whereas the jump takes 200 picoseconds. Remember the jump? It exercised only that upper part of the data path, right? So even with these optimistic assumptions, you get very wide variance in terms of different types of instructions in a single cycle microarchitecture. And I'll let you figure out the critical path for each of them. But if you look at the R-type and I-type ALU operations, there are 2 things that happen concurrently in the single cycle microarchitecture for these instructions. One is the ALU operation itself, which does form the critical path. Well, I guess it's instruction fetch plus decode plus register file access plus ALU execute. You bypass memory, and then this is the 0 picosecond assumption, right, with the mux that we had. That's why you don't add some time. And then you write to the register file. So it's 400 picoseconds. But there's something else that also happens, which is the incrementing of the program counter. But that's only, well, at least with the values, with the cooked up values that I gave you, it's only 100 picoseconds. So this is your critical path for the ALU operation, 400 picoseconds. For load word, it's much longer because it does exercise, in addition to everything else that the R-type and I-type ALU operations exercise, it also exercises memory, right? Okay? And store word. Okay, you got the idea, right? I'm not going to go into this in more detail. Basically, you can all do critical path analysis. Yes? Or should we cover this a little bit more? Yeah. Okay. You can go through. Let's cover, I guess, branch taken also. Branch taken is interesting because I guess there are two things that happen. First of all, you need to calculate the address somehow, which goes through the ALU, because you take the program counter and add to it some value. Sorry. You need to calculate the address, which I guess address calculation can go through the ALU also, but we have two different adders right now. This is the address calculation, right? You take the program counter and add to it a sign extended left shifted immediate. That gives you the address, which is the data input for this mux. And according to the numbers I told you, an adder takes 100 picoseconds, and another adder takes another 100 picoseconds. So within 200 picoseconds, the data input for this mux is ready. But you also need to determine the branch condition, right? Whether or not the branch is taken. And that is determined through the register file. You need to read the registers. You need to compare the two registers, depending on the opcode. You do different comparisons. And based on the result of the comparison, then you choose either the output of this adder or PC plus 4, output of this adder. Right? So this control input arrives much later than this data input. So this is the critical path. And then there is muxing, and we assume that that muxing takes 0 time. So the critical path of the branch taken operation is really 350 picoseconds. Okay? And you could do the same thing for jump. Again, jump has a data input and a control input. And again, control input arrives later, at least in this case. Okay. Basically, there are some cases where actually the control determines your critical path, not only data, right? What about control logic itself, though? This control logic, does it determine your critical path? Are there cases? I'll let you think about it. In most cases, your data path is your critical path. But if you think about generation of the control signals, that could be on your critical path also, right? If it takes too long to generate a control signal, too long to decode an instruction, that could be on your critical path too. That's usually not a great design, though. You don't want your control logic to be on your critical path. Now here, the control logic is on the critical path, but it's dependent on a data input, right? Your control is really, the control of this mux is really determined by whether or not the branch is taken or not taken. But I'm talking about this control logic that generates the control signals, taking just the instruction bytes as the input. Sometimes your control interacts with your data. In case of a branch, for example, when you determine the condition of the branch, you need to look at the data. Right? Okay? So can control logic be on the critical path? Yes. This block can be on the critical path, even if it's combinational or sequential. In fact, one of the earlier machines, CDC 5600, this was Control Data Corporation. They were competitors to IBM in the 1960s. This was a very small company. I think maybe 50 or 100 engineers or so. They were competing with this huge company, IBM. And they had, this is one of their earlier machines. In the later machine, they implemented out-of-order execution. And they beat IBM in terms of their performance with a very small number of engineers, which prompted IBM to design their own out-of-order execution machine, which we will cover later. It's called Tomasulo's algorithm. Robert Tomasulo designed Tomasulo's algorithm. But this was Control Data's machine before that out-of-order machine that they designed. And it turned out their control store, they had this kind of a control store. Their control store access was too long. So that determined the cycle time, so they broke it up into multiple cycles. Make sense? Okay, so what is the slowest instruction to process? We've seen it with these cooked up values. But I guess I've given you the answer. I should have asked too. Too bad. We assume memory is magic, right? But memory is not magic. And memory is usually the bottleneck in terms of latency in your systems. What if memory sometimes takes hundreds of milliseconds to access? Well, does it make sense to have a simple register to register add or a jump to take 100 milliseconds plus all else to do a memory operation? And the answer is no, right? And what if you need to access memory more than once to process an instruction? Which instructions do this? Are there instructions that access memory more than once? Load word, right? Yes. Why? Because you need to fetch the instruction, access memory, and then you need to get the data value that you need to load. Do you provide multiple ports to memory? I'll let you think about that. We'll cover ports later on, but you may need to. Okay, so let's wrap up single cycle microarchitectures. The main problem is it actually looks simple, but it's very complex to design. First of all, it's contrived. All instructions run as slow as the slowest instruction. But this leads to inefficiencies also in the microarchitecture. Not only that, but now you must provide the worst case combinational resource in parallel as required by any instruction, right? Whereas if you took multiple cycles, you could reuse some of those resources. So your hardware cost may be very high with a single cycle microarchitecture because you cannot reuse resources across the execution of the same instruction, right? Yes, so you need to replicate a resource if it's needed more than once by an instruction during different parts of the instruction processing cycle. If you need the adder, for example, multiple times, you cannot just have a single adder because you have to do two adds, for example. Well, which instructions do two adds? For example, if you're actually incrementing the program counter as well as adding registers, right? If you had multiple cycles to do this, you could use the same adder to do both. Now, we didn't do that because it's a single cycle microarchitecture. Okay. This is also not necessarily the simplest way to implement an ISA. Think about these things. Remember these instructions? What if you have a complex instruction set? Repeat, move S. You're doing this for your homework. So you don't want to have a single cycle microarchitecture doing repeat, move S probably. And it's not easy to optimize or improve performance because you don't have a degree of freedom, right? You're not really optimizing for the common case. So let's say you have most of your instructions are adds. You really want to optimize your microarchitecture for those adds so that you can execute them very quickly. But now you need to optimize for the worst case, a memory operation that takes maybe repeat move S, right? You need to reduce how long it takes to do a repeat move S to optimize your performance. Now this is terrible. This violates a basic principle in microarchitecture design, which is you really want to optimize for the common case. Right? Actually, that could be the basic principle in engineering, right? If you want to maximize some performance, you want to find the common case and optimize for it first. And then something else becomes the common case, right? This is more bottleneck analysis. You find the bottleneck, you optimize for it, and then something else becomes the bottleneck. Whereas here, your bottleneck is the worst case, right? Even if something is not common, it's determining your performance. So that brings me to microarchitecture design principles. There are 3 principles. I guess if you get one thing out of this lecture, you get these principles. There are 3 key principles in designing a microarchitecture. One is critical path design. You would like to minimize a critical path. Right? Find the maximum combinational logic delay and decrease it. This always improves performance, almost. You don't want things taking longer than they need to take. Right? Second thing, and this is actually true. You want to do this in a single cycle microarchitecture too. Actually, you want to do this really badly in a single cycle microarchitecture because you have only a single cycle to deal with. The second thing that is violated by the single cycle microarchitecture is common case design, or this is called bread and butter design as well. Basically, spend time and resources where it really matters. Right? Don't optimize for what's taking 0.1% of your execution time. Optimize for 90% of your what's taking your 90% of your execution time. Right? That's the idea. Basically, improve what the machine is really designed to do, what the machine is really executing, which means that you somehow need to find the common case versus uncommon case. And finally, the third principle, this is for designing a good microarchitecture, is a balanced design. What is that? Basically, balance the hardware needed to accomplish the work. You don't want too much hardware in your system. Also, this actually can mean multiple things, but also balance the instruction and data flow through the hardware components. You don't want many hardware resources that are just not utilized, right? Or you don't want a single bottleneck in your hardware. For example, if you have the ability to fetch 5 instructions per cycle, don't have just one execution unit, right? That's not a balanced design. Vice versa may not be a balanced design also. Here, I guess I'll pose you the question, how does a single cycle microarchitecture fail in light of these principles? I would argue that it violates these two principles very heavily. It violates balanced design because now you need, well, let's go back. I've already given you the answer for this, right? You need to replicate a resource. Right? You cannot design a minimal microarchitecture. You cannot have a single adder. If an instruction does 100 adds, you have to have those 100 adders. Right? So it's not a balanced design. And it's definitely not a design for the common case. Okay, any questions on these? This is something you should probably have ingrained going into the rest of the course, because you're going to be doing a lot of designs later on, both in Verilog as well as C. So keep these in mind for sure. Especially in Verilog, for example, critical path design, some of the designs that you will do will look at your critical path and will give you extra credit if it's very fast. So you'll get a chance to optimize your designs this way. And you will get a chance to optimize your common case also. You'll get some extra credit to improve the performance of some of your designs. I guess balanced is a little bit harder to evaluate. But we'll cover this when we talk about superscalar architectures. When you fetch multiple instructions per cycle, you want to ensure that the flow of instructions works well. Okay. So let's go into multi-cycle. Basically, the goal in multi-cycle microarchitecture is simple. Let each instruction take only as much time as it really needs, right? And no more. Well, hopefully close to that, because there will be overheads, right? The idea is you determine the clock cycle time independently of the instruction processing time, right? Break the instruction into multiple stages. And each instruction now takes as many clock cycles as it needs to take. Multiple state transitions per instruction, and the states followed by each instruction is now different. You've already seen the slide, the process instructions step, so I'm not going to cover this part. But at the ISA level, you have one state transition per instruction, right? That's what the programmer sees. Architectural state changed into another architectural state. At the ISA level, this is nice. But microarchitecture can do this, right? This is the multi-cycle microarchitecture. You take the architectural state, transform it into different microarchitectural states, and output another architectural state in the end. This is another way of looking at it. I'm going through this relatively fast because we've covered a lot of these slides earlier, and I want to get to microcoding quickly. But if you have questions along the way, feel free to ask. So what is the benefit of a multi-cycle design? Let's take back these principles. You can evaluate any microarchitecture using these principles. Critical path design. Is there a benefit? Well, now you can keep reducing the critical path independently of the worst case processing time of any instruction, right? Now you've decoupled your critical path from the worst case processing time of an instruction. You can have an instruction take 1 million cycles, but the cycle time can be very short. Okay? Bread and butter design, common case design. Well, this should be obvious now. You can optimize the number of states it takes to execute important instructions. Right? Now you can focus your efforts. If most of your instructions are adds, now you can go and look at how many states it takes to execute the add, right? And minimize that. If most of your instructions are repeat move s for some reason, you can go and optimize that. But optimizing that is easier now, right? You optimize the number of states. Balanced design, now you don't need to provide more capability or resources than really needed, right? Because you're, again, using the hardware across different states, reusing the hardware across different states. You can have the minimal hardware and use that hardware over and over in different cycles, right? So it's a lot more beautiful, right? You could argue that it's a lot more simple too. Okay. Yeah, I think I've already given you this. Okay, let's get back to that performance analysis slide that we have flash forwarded to early on. Remember, the execution time of an instruction is cycles per instruction times clock cycle time. Let me see if I need to. Oh, different things start appearing here. I don't know what this means, but you don't need to know this. So that's the execution time of an instruction, right? Cycles per instruction times clock cycle time. Clock cycle time is essentially, you can think of this is in terms of seconds, right? And this is how many cycles it takes to execute an instruction. But let's take a look at this. An execution time of a program is really sum over all instructions of this. For each instruction, you have this value, right? Which is number of instructions times average cycles per instruction times clock cycle time. This is also called the performance equation. We will see many different ways of optimizing this over the course of this course. If you look at the single cycle microarchitecture, we've seen that CPI is 1, clock cycle time is long. But multi-cycle microarchitecture, CPI is different for each instruction. Right? How many cycles it takes to execute an instruction is different. An add maybe takes 2 cycles. Well, we'll see in the LC3B microarchitecture, it's a little bit more than 2 cycles. But a load may take 100 cycles, right? Or longer. But average CPI is hopefully small, and you can optimize for that. And clock cycle time is now short. So now you have 2 degrees of freedom, right? This was not free before. Now this is free. I guess while we're at it, I'll give you another thing, which is CPI versus frequency, right? CPI is cycles per instruction. And clock cycle time, what is this? This is 1 over frequency, right? Of the machine. These usually are at odds with each other for the processing of a single instruction, right? Reducing one increases the other. And this is pretty intuitive, right? Like why? Intuition, you can say. But the reason is basically if you reduce, there's some amount of work that you need to do to finish an instruction, right? Work. Let's say that work is n nanoseconds or so. Somehow you come up with this amount of work. Basically what you're doing is you're dividing this amount of work across multiple cycles, right? Which means that if you reduce your clock cycle time, you'll take more cycles to execute the instruction, right? So that's why CPI and clock cycle time are usually at odds with each other. And you'll see this. There are other reasons for this also in pipeline microarchitectures. So there's another thing. Average CPI, average cycles per instruction. Let me write the performance equation again. Basically, execution time of a program can be expressed as number of instructions you have in the program times average cycles per instruction times, well, so I'll do this, times clock cycle time, right? So this average cycles per instruction, you can improve performance in 3 different ways, right? We discussed this briefly last time. You can reduce the number of instructions. You can reduce the average cycles per instruction. And you can reduce the clock cycle time. Ideally, you would like to have everything like this. But usually, it's a trade-off. And I've given you one trade-off, right? CPI and clock cycle time are at odds with each other. Because if you reduce the clock cycle time, because you have fixed amount of work to finish an instruction, you're usually increasing cycles per instruction, right? But you can get away from this. As an architect, you can be creative, right? You can say, oh, why not process multiple instructions at the same time? If you do multiple instructions, basically you're amortizing the same cycle in one cycle. Let's say you're doing 2 instructions. Well, it's nice, right? Your average cycles per instruction goes down. Maybe you don't change the clock cycle time if you do that. Hopefully. If you provide additional hardware, obviously you need additional hardware to execute multiple instructions per cycle, right? You cannot reuse the same hardware if you're executing for the different instructions if you're executing multiple instructions per cycle. So think about these trade-offs. But basically, we will see many methods to do this. The same cycle is devoted to processing multiple instructions. And actually, pipelining does that, right? We'll see this in more detail. But in pipelining, what you're doing is in the same cycle, you're executing different instructions, except those different instructions are in different phases of their instruction cycle. While you're fetching the add, you're decoding a multiply, for example. While that multiply is being decoded, maybe you're executing a load. And at the same time, maybe a divide is storing its result, right? So that's what pipelining does. It reduces this. But then there are overheads also. Usually, even if you execute multiple instructions per cycle, you have the overhead of increasing the clock cycle time. If you reduce cycles per instruction, you usually increase clock cycle time. And we will see this. For another option is having superscalar execution. You fetch multiple instructions per cycle, you decode multiple instructions per cycle, and you execute multiple instructions per cycle. Now this is nice because if you're doing this perfectly, your cycles per instruction goes down, right? Let's say you're doing, for example, today's Intel processors usually fetch, decode, and execute 4 instructions per cycle. There have been machines that were designed, IBM Power 5. They can fetch 8 instructions per cycle. Well, it's nice, right? You reduce this. But it's not free. It actually affects this usually. Why? Well, the machine somehow needs to determine whether or not it can execute all those 8 instructions in parallel. Right? What if those instructions, let's say you have add R1, some source, multiply, sources of that. Well, I guess I won't give you all the sources. You have another add that sources the result of this multiply. So you have dependencies between instructions. This is called a dependency. A later instruction sources the value written by a previous instruction. Let's say you're fetching, 4 instructions per cycle. This is ugly, right? The machine somehow needs to determine which instructions can be executed at the same time. And in this case, even if you fetch all of these instructions in a single cycle, you cannot execute them in the same cycle, right? Because these instructions are dependent. The later instructions are dependent on the previous instructions. Well, somebody needs to figure that out. So there's additional hardware in a superscalar machine that figures out whether this multiply is actually dependent on the add. Whether this add is actually dependent on any of the previous instructions that are fetched concurrently. Whether this load is dependent on any of the previous instructions. Now you can imagine the complexity of that logic, right? Can you guys guess? Basically, you need to take all of the operands of a later instruction and compare it to all of the destinations of the previous instructions. And as you increase the number of instructions you fetch concurrently, this logic becomes quadratic, right? You can think about that. But this is exactly the reason why, if you increase it, well, this is one example. If you reduce the cycles per instruction, you need that extra logic to figure out whether the instructions are dependent, which does affect your clock cycle time. Now you can say, I'm going to add another pipeline stage, not affecting my clock cycle time. If you add another pipeline stage, it turns out you're increasing the cycles per instruction again, right? Because it's taking longer to execute that cycles per instruction. So it's a trade-off. As an architect, you're trying to balance these different trade-offs. Same thing we discussed, right? Number of instructions you can reduce by making the instructions more complex. Now, when you make the instructions more complex, that affects your cycles per instruction, right? If you make the instructions simple, you reduce the cycles per instruction, but you have more instructions. So I'll let you think about different trade-offs, but keep this equation in mind. We'll use this a lot when we talk about out-of-order execution, for example. Think about how it affects these three different things. And different implementations of superscalar machines, pipelines, out-of-order execution engines, all differently affect these different components. But this is another fundamental thing that you can have in your repository, I guess, as an architect. Okay. I guess let's take a break for 5 minutes right now, and then we'll go into a microcoded machine, a multi-cycle microarchitecture. And that's described here. That's probably why Maurice Wilks called it the best way, right? Okay. So the realization is one can implement the process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. I guess I'll shuttle back and forth between these things. But this is from your Appendix C. What is Appendix C? It's from your readings. Okay, now you know Appendix C. And this is this, oh, I always make the same mistake. This is the finite state machine of LC3B, one implementation of LC3B. Well, let's see if we can fit everything here. It's nice, right? There's only 31 states. We would love to be able to implement x86 in 31 states, but that's not going to happen, I think. But yes, basically that's the realization. You can implement this step as a finite state machine that sequences between states. And somebody determines that sequencing. Well, what is that? That's the control logic. The job of the control logic is to determine what state comes next, plus what control signals need to be asserted in each state. Basically, a state is defined by the control signals asserted in it. That's the definition of a state here. And control signals for the next state are determined in the current state. And we'll see why this is important, because you don't want to put that on your critical path. And I'll give you examples of this. So basically, you have this instruction processing cycle. You break this into stages. Well, you have 6 stages here. But you can have multiple states implement each processing cycle. For example, if you look here, these 3 states are actually the fetch phase. It takes 3 states, 3 cycles. Well, it's not exactly 3 cycles, actually, because you're accessing memory here. Now you can have arbitrary memory latencies, right? The data path stays in this state, the machine stays in this state until memory becomes ready. Can you guys see that? You have much better eyes than I do. Let me try to zoom in a little bit. And for some reason, this printout prints these boxes. Anybody know why? That shouldn't be a box. This should really be an arrow. I don't think this is like that in the PDF file. It's really my printout. Anyway, that I think for now, rename in your mind that box is really a dash. Okay, so that's the fetch state. This is the decode state, and you have different control signals associated in each state of the state machine. And we'll cover some of these. We'll actually write the microcode for one instruction, probably in the next class. And you will actually write the microcode for the entire states. So it'll be fun. OK, evaluate address is another state. Depending on the instruction, you may or may not have this. But for example, another state here is evaluate address, which is, I will hopefully be able to find that. Where is this load instruction? Yeah, load byte instruction, for example. This load byte instruction, there is one state that evaluates the address. MAR, memory address register, gets the base register plus offset 6. OK? And execute. For example, execute for the XOR instruction. This is the execute stage implemented in a single state. Store result. Well, store result happens to be in the same state as execute. If you can write to the register file, and if that doesn't take too long, right? OK? Basically, instruction processing cycle is divided into states. A stage in the instruction processing cycle can take multiple states. As I showed you, fetch takes 3 states here. And it can take more than 3 cycles. And a multi-cycle microarchitecture basically sequences from state to state to process an instruction. That's what you're doing, sequence from state to state. And the behavior of the machine is completely determined by the control signals in that state. And we will see what those control signals are. And the behavior of the entire machine is fully specified by this finite state machine. You could actually do this if you want to design a microcoded x86. You could do this for the x86 also. You could have a single state machine that implements all of the x86 instructions. Would you prefer that to be your lab assignment? Probably not, yeah. I agree. That would be tedious. But having said that, something like this exists in your x86 processors today. For example, repeat moves is implemented this way. Or very similar with the same principles. Not all instructions are implemented this way in x86, by the way. Some instructions are implemented in a different way. But we'll cover that at some point. So in a state or a clock cycle, control signals control how the data path should process the data. They also control how to generate control signals for the next clock cycle. Because now you have multiple clock cycles, right? And your control signals determine what your control signals should be in the next cycle, plus some other signals determine what your control signals should be in the next cycle. And those other signals come from your data path. One example. Here, for example, this state, we put the program counter into the memory address register, which we will see, because we want to fetch the instruction. And we're incrementing the program counter. Ignore that for now. In the next state, the transition is unconditional, right? Once the machine goes into this state, the memory address register has a program counter. The next state is read memory. Now, in the next state, state 33, the transition is conditional, right? Next state is determined by not only this current state, but also whether this R bit is set or not set. Now, what is that R bit? That R bit comes from memory, and that says, is memory ready? You've already put an address into the memory, and you're reading from memory, and memory can become ready asynchronously now. It could take 100 cycles. During those 100 cycles, this machine will stay in this state, waiting for memory. So the control signals for the next state will be the same as the current state, if that ready bit is not set. Right? Because remember, a state is defined by its control signals. Once that ready bit is set, then the control signals for the next state would be different. And the next state itself is different, 35. Okay? So some terminology. I'll give you some terminology in microprogram control. You will see this in many places. But control signals associated with the current state are also called the micro-instruction, the set of control signals for that current state. This is the micro-instruction. The act of transitioning from one state to another, determining the next state and the micro-instruction for the next state is called microsequencing. You'll hear the term microsequencer. In fact, Intel and AMD processors have this microsequencer inside. They sequence to a next state. Control store, you've already seen this. Well, it's hiding now. Let's see. There you go. Control store. It may not be only indexed by IR. In fact, we'll see that it's indexed with other things. These store the control signals for every possible state. So in this case, we see 31 states. So we'll have a control store that store the control signals for 31 states. Basically, this is a store for micro-instructions for the entire finite state machine. And there's a microsequencer that determines which set of control signals will be used in the next clock cycle. So if I show you this first picture, that will complete a lot of things, I think. Oh. OK. So this is the entire LC3B microarchitecture, microprogrammed with bigger blocks. This is your control store. Each entry corresponds to the micro-instruction for that state. And these are the control signals. This is the micro-instruction for the current state. These control signals determine how the data path operates. They also determine what the next state should be, partially, because next state is also dependent on what's going on in the data path. For example, if the memory is ready or not, if the branch should be taken or not, what instruction we're processing, right? That's the instruction register. Okay. Why do you need this? Well, when you're decoding an instruction, you'd like your control signals for the next state to be determined by your instruction register, right? Make sense? And this is the control store. Basically, using these signals, you index the control store, get the micro instruction, and those are the control signals for the next cycle. Okay? And this control consists of control store and the microsequencer. Let's see if the I'll get to that picture. But what happens in a clock cycle? If you look at this, what do you have going on in a clock cycle? These control signals that are latched in a register in the current micro instruction determine what goes on in the data path, the processing that goes on in the data path, which muxes are adjusted which way, what should the ALU do, right? They also determine the generation of control signals for the next cycle. Basically, while you're processing in the data path, you're indexing this control store. You have some combinational logic that sequences to the next state in the control store, and you're also accessing the control store to get the control signals for the next cycle. Make sense? So now our control and data are decoupled. Right? Remember, in a single cycle microarchitecture, you have to generate the control signals the same cycle you're processing the data. Right? Here, data path is doing something. At the same time, you're determining your next set of control signals. You're parallelizing. You're parallelized control and data. That's one benefit of this. Well, I'll get to that supplemental figure. I guess I cannot put multiple figures everywhere. Right? Maybe you guys can come up with a solution to a better display here. OK, so basically, data path and microsequencer, or control, operate concurrently. Well, I think I've already given you the answer. You don't need to repeat it. But why not generate control signals for the current cycle in the current cycle? Well, that lengthens your critical path. That would be one of the major mistakes in designing a microarchitecture like this. Why would it lengthen the clock cycle? Well, because control signal generation doesn't take zero time, right? And you will see this. Let's take a look. I like thinking of it abstractly this way. You have cycle n, and you have the next cycle, right? In cycle n, we've covered what happens, right? Processing in data path for cycle n happens, and generation for control signals for cycle n plus 1 happens, right? And at the end of cycle n, you latch the results of the current cycle n, and you also latch the control signals needed for the next cycle n plus 1. That's it. You stagger, basically, control and data processing. Well, if you do the bad alternative, you generate the control signals for cycle n in the same cycle as processing for Datapath. In the same cycle, you need those control signals. Well, there's a dependency between these two, right? Step 1 is dependent on step 0, and if step 0 takes non-zero time, and I'll guarantee you that it will take non-zero time, clock cycle increased unnecessarily. Right? This is a bad design. So why is it a bad design? Let's go back to the principles, right? It violates the critical path design principle, right? You haven't thought about your critical path. Whereas a very simple way is to decouple those, stagger those. Data processing, you generate the control signals that you need in the next cycle in the current cycle. Now, you may not be able to do that for every single control signal, right? So you minimize those control signals, or you minimize the effect of those control signals on your critical path. Yes?
What if we design the opcodes in such a way that the control signals are passed through in the instruction code?
Oh, so now you're going to that open microcode concept of John Cock, right? Why not have your instructions specify your control signals? Yeah. Yeah, I mean, there are advantages to that also, right? Now it simplifies your control in hardware. Maybe it simplifies your critical path too. That's one of the reasons that was proposed by John Cock at the time. This is in the spirit of reduced instruction set computers. Now, the instruction may become more complex. You may need to encode more things, but the instruction is much closer to your hardware, right? Remember that picture, semantic gap picture, that I drew several times? If your instruction specifies most of your control signals, then most of what you do in microarchitecture is data path processing. Now, you cannot do it perfectly, right? Because there are some control signals, for example here, that need to be determined based on the execution. But yes, that's a very good point. And you're thinking like John Cock now, probably, when he thought of it in the 1970s. OK. Well, I guess now we have two copies of the same picture. But this is the simple LC3B control and data path. It's a microprogram control that you will get to know and love, hopefully. So what determines the next state control signals? If you look at this box determines the next state's control signals. Basically, what comes here? What is an input to the box? What is happening in the current clock cycle, as I told you, right? Let's see. See the 9 control signals coming from the control box. This is this. These are the control signals that, these are the current control signals that determine partially what is your next state. And we will see this. For example, actually, maybe I'll get to the microsequencer right now. For example, one control signal is IRD. And that IRD tells you whether the current state is actually the decode state, whether you're decoding an instruction. And based on that, your next state is dependent on what's the outcome of the decode, right? So let me, if you will understand this much better once you read the part, but this is what the microsequencer looks like. This is how you determine the address of the next state. Now, address of the next state, what does that mean? Remember the control store? Let me modify this control store picture here. So this is your control store. This is the next state address. You index the control store with the next state address. And you need to somehow determine the next state address and access the control store. And at the end of the clock cycle, you latch the micro instruction associated with that next state address. And what's stored in the control store is the control signals for that next state. So somehow you need to determine the next state address. How do you determine? Well, this is the structure that determines for LC3B based on your state machine. What determines that? For example, this IRD signal tells you that the next state address should come from this. If the IRD signal is not set, next state address should come from this mess here that you will learn again. But I'll give you an example. Why is this? Let's say IRD is set. then your next state is 0, 0 concatenated with top 4 bits of the instruction register. Now, if you remember LC3B ISA, what are the top 4 bits of the instruction register? Anybody remember? Those are the opcodes, right? Top 4 bit is always the opcode. And let's get back to the state machine now. There is a state in the state machine where the next state is very much dependent on the opcode. Do you see that? Yes. Which one? You can see it, but can you read it? That's state 32, right? In state 32, next state can be many. Actually, there are 16 possible next states, I think, some of which are not shown here. And those 16 possible next states are dependent on the opcode. For example, if IR 15 through 12 is add, which is opcode 0000, I think, then you go to this state. Well, that's what your microsequencer determines, basically. In that particular state, in state 32, I'm sorry, that decode state, in the control store, this IRD signal is set to 1. Basically, you have this micro instruction that has 35 bits. One of them is IRD. 1 bit here is IRD. It's set to 1 in state 32. State 32, let's just take a look at that signal. It's just 1. And while you're in this state, this IRD signal goes to that MUX, right? In the data path, you have the instruction register, right? And that instruction register feeds that MUX. And the next state address is essentially determined by the opcode of the instruction. And, well, I guess that's how it is, right? Now we're building the machine. So in that particular state, next state is determined this way. Simple for that particular state, right? And state encoding will hopefully have the correct microinstruction for the next state, right? So that's how you can program this machine, basically. For each state, you figure out the value of each control signal for that particular state. Okay? We'll do this more often, so you'll get used to this. If it's not, yes?
When you say next state address, that's not literally an address in memory, correct?
It's not an address in memory, you're right. It's an address in this control store. Yeah. Okay? Although, you could stretch your mind a little bit and think about storing it in memory also, right? Now, you don't want to do that probably because that's a lot of additional complexity and it takes time to get your control signals now. But this is a specialized memory that's present within the chip. Okay? Okay. Let's get back to this. But now we've actually microprogrammed one particular state. Right? Actually, we didn't program all of the bits in the control signal, but I showed you one way of how you can determine the next state for a given state. Now you can imagine for all other states, IRD bit is not set. Because there's only one state in the state machine where you decode the instruction, right? And that's this. For all other states, the next state is determined. Oh, let me see if our microsequencer is here. Okay, I guess I won't be able to get to that. So let me do this. For all other states than state 32, the control signals, the next state address is determined by this logic. Right. Okay, and we'll take a look at that. Well, let's get back. Let's rewind the stack a little bit and look at what else determines the next state. Well, I guess the instruction that is being executed, we've already seen that it can determine the next state. Whether the condition of a branch is met if the instruction that's being processed is a branch, that also determines the next state. That's this branch enable bit. If you're branching, that can determine what is your next micro instruction, right? Make sense? Whether or not a branch is taken or not taken determines that. Actually, let's take a look at that in the state machine. There you go. This depends on the design of your state machine, of course, but given that there is a state machine design, we're not going to change it now. But here, this is the state. So you figured out your instruction is a branch. So in this state, the next state is the state that executes the branch instruction. And there's a branch enable signal that was pre-computed in the previous state. It happens to be, according to the specification. And if you look at the LC3B ISA, the branch computation is based on condition codes. You guys know what condition codes are? Yes? Some of you do. That's good. Basically, when an instruction executes, it can set a condition showing the value of the result. And in LC3B, there are 3 condition codes: negative, 0, or positive. When an instruction finishes execution, its result is checked. There's some logic that checks whether the result is negative, 0, or positive. And only one of them can be true, right? And the corresponding bit is set depending on the result. And the branch, the semantics of a branch in LC3B is basically if you're branching on the negative bit, there are different kinds of branches. You can branch on any combination of these bits being true. Branch negative, for example, checks if that condition code is negative, if the negative condition code and condition code is set, then branch. Otherwise, go to the next instruction. That's the semantics. So there's some logic that needs to compute whether the condition of the branch is met. Right? And that's computed in this state. Well, why is it computed in this state? Because maybe you don't want this logic to determine your next state's control signals later. Right? Okay? This is another, again, you're trying to overlap the next state computation earlier. You don't want to have that be on your critical path. So if you look at the branch enable bit, here you have the branch enable bit is set. In this state, this branch enable bit determines what the next state is. If the branch enable is 0, meaning branch should not be taken, the next state is basically fetch. You've already incremented your program counter. If the branch enable is set to 1, then the next state computes the program counter based on the branch instruction, which is program counter plus left shifted offset 9, 9-bit offset. Does that make sense? So this is how your branch enable bit determines what your next state is. At least in this microarchitecture. You don't have to design it this way, right? But this design is elegant because branch enable is computed much earlier. In this state, you only need to check branch enable. That's it. OK, let's see. There's also, well, we've already seen that, whether the memory operation is completing in the current cycle if one is in progress. That's the R bit coming from memory. And that is also an input to your control store. Now we're going to cover the data path. So far I've been treating it as a black box, but we will see that also. OK. So the behavior of this LC3B microarchitecture is completely determined by the set of control signals, 35 control signals, and this additional 7 bits that go into the control logic from the data path. Right? And this 35 control signals completely describe the state of the control structure at that point in time. Which means that you can completely describe the behavior of LC3B as a state machine, as a directed graph of nodes and arcs. Right? A node corresponds to a state, and arcs show the flow from each state to the next state. And this is your state machine, which I've already shown you. Let's zoom out a little bit so that you can see the entire thing. But I guess you all know what a state machine is, right? You've dealt with it very, very well in 240. So I'm not going to cover all of these. But if you look at this, this actually has 31 distinct states encoded with 6 state variables. Here, the state actually has 2 addresses in the control store. You have states 18 and 19 corresponding to the same logical state. And I'll let you figure out why that is the case. Any guesses why this could be the case? Why do you want to have 2 control store entries for the same state? Yes?
Yeah, more signals that can fit. There's more control signals. Never mind. So,
I didn't quite understand that. But maybe. So the reason is you need to get to this place from multiple places. And I guess it's not apparent here. Well, it could be apparent here. I don't know which one is 219. There you go. Yeah. So all of these states that end an instruction, that finish the instruction processing cycle, need to go back to fetch, right? So if you look at this, this is the add instruction. Add instruction finishes the add, sets the condition codes in this state, and then the next state is 18. This is the AND instruction. Finishes the AND, sets the condition codes, next state is 18. ... You have many of these instructions finishing, and they all need to go back to 18. Well, maybe the encoding is not easy to specify as 18. So here, especially when the next state is conditional, it's easy here, right? The next state here is not conditional on what's going on in the data path. If you're in this state, the next state is always 18. Right? So how can you accomplish that? Jumping, let's just take a look at that in the microsequencer. I'll have to find the microsequencer first. Okay, there is your microsequencer. Basically, that state, when the add instruction finishes, the next state is state 18. Right? How do you encode state 18? Well, these J bits tell you what is your next state. So you unconditionally go to what is specified by these J bits, which are set to 18 in that particular state. Does that make sense? Basically, you set the J bits in the control store to 18, set IRD to 0 to select the J bits, and ensure that none of these mess up the J bits. How do you ensure that none of those mess up the J bits? Well, the next state transition is not conditional. Next state transition is always state 18. So you set the condition bits such that these AND gates always evaluate to 0. Right? Make sense? So that's how you implement an unconditional state transition. Now the problem is, what if sometimes you have a conditional state transition? So if you look at this, there's one case in the state machine. Because the state machine is designed this way, and these are the cases. This is the store word and store byte instruction. You have 2 instructions that store. Once the store is done, you go back to state 18. Once the store is done, you still want to go back to state 18. Right? But these transitions are actually conditional. Here, you encoded your states such that this is state 16, 17. From both of those states, you want to be able to go back to state 18. But the transition is conditional. It's dependent on this ready bit. Right? Well, state 16, if the ready bit is set, the next state should be 18. How do you ensure that? If you go back to the microsequencer, you have a conditional transition. So if you look at the microsequencer, the next state, while you're at state 16, the next state could be state 16 or 18, right? And the next state depends on the ready bit. So you set J bits to 16, and the next state is conditional on ready bit being true or false. So you set the condition bits such that condition 1 is 0 and condition 0 is 1, right? You take into account this AND, the result of this AND should always evaluate to R. Make sense? Now, from both state 16 and 17, you would like to be able to, at state 16, you'd like to be able to go to state 16 or 18, depending on the ready bit. And state 17, you'd like to be able to go to state 17 and state 18, because state 18 is fetch, remember? And if you go back to this, where's our finite state machine again? I'm talking about these two states that I've just shown you. This is state 16. You conditionally go to state 18. And state 18 is fetch. The instruction is done because you've stored to memory. State 17, the next state is either 19 or 17. Well, the reason that this is 19 is because you cannot do this conditional thing to state 18, right? If your current state is state 17, and if you're dependent on the R bit of memory, your next state encoding has to be state 19, right? If this R bit is set, and if your J bits are state 17, you either stay in state 17. If your R bit is set, your state should be 19, right? So that's why that state is encoded as 19. Does that make sense? Now you could argue that you can have a special case, right? Meaning, if you're in this particular state that's state 17, and if your R bit is set, then your next state should be state 18. Well, that complicates your microsequencer now, right? That makes your microsequencer more complex, and your control logic will take much longer. So you have all the design freedom, but the choices you make, the encodings, the choice of the encoding you make in the state machine also determine how elegant and how simple your microarchitecture is. Okay, so let me finish at some point. I guess I'll leave you with some questions, and then we can finish. So I've given you some examples. State 18 and 19 correspond to the beginning of the instruction processing cycle, and I've told you why you have 18 and 19. But again, that's a choice you made. That's a choice the designers made here. Fetch phase. Let's just look at the fetch phase quickly before we part. If you look at the fetch phase, it consists of these three states: 18, 19, 33, and 35. And we'll see how we sequence between them. Decode is state 32. Because how many cycles does the fastest instruction take in this? 4. 1, 2, 3, 4. I guess let's ignore these instructions. These are actually, well, to state, what is this? To state 8. If you figure the state 8 actually doesn't exist in this machine. That's going to be added later. So don't worry about it. This is actually a return from interrupt. So there's something that happens. Ignore these instructions that do not go to any states. So it's actually 1, 2, 3, 4, 5 states, right? Fastest instruction. But that's not the same thing as cycles, though, right? Because you have these conditional transitions, right? So assuming your memory takes 5 cycles, then the fastest instruction takes 1, 5, that's 6, 7, 8, 9 cycles, right? Okay. How many cycles does the slowest instruction take? Well, I guess I'll let you figure that out. What is the slowest instruction first? Assume that the memory is 100 cycles. Okay, I think I'll let you study these questions. What determines the clock cycle is not the instruction, but hopefully this will give you some brush up on your logic design also. Is this a Mealy machine or a Moore machine? You guys remember what those are? You don't? You haven't studied in 240? Say it again?
I have no idea.
You have no idea? All right, this will be good homework then. A Mealy machine, basically, a Mealy machine is a machine where the output, yeah, go ahead.
Output generated on the transition.
So output is dependent on, is not only dependent on the state, basically. Whereas a Moore machine is, the output is a strict function of the state only. Okay? Input, exactly. Yeah. So a Mealy machine is a machine where the output of the state is a function of the input as well as the state itself, whereas Moore machine is a machine where the output of the state is only determined by the state, which means that Moore machine actually has more states if you want to implement the same functionality. OK, I'll see you Wednesday.